So in this video I'm going through task 4 of the waves unit 2 ISP. So it's moved on from the light part of it, we're still in the waves part of it. So now we're on 2. Describing the process of superposition, describing the formation of stationary waves and comparing them to progressive waves. So we did a bit about in the last one, but we're still doing that here. And talking about reflection, refraction and diffraction essentially, and the idea of refractive index. Remember, total internal reflection ties in with this. Those of you going for the AA start need to research the idea of Broglie diffraction, which ties in when we cover diffraction. Remember, that's to do with particles behaving as waves as well as wave behaving like a wave. Particles behaving like a wave and therefore diffracting. To quickly cover that, the idea is that the faster a particle is travelling, the greater the momentum it has, and therefore the smaller the wavelength it has, therefore it can diffract through small gaps. And that can allow it to diffract. So we can use that to investigate the structure of matter. So let's get stuck into the explaining everything for number 4. So if I remember correctly, this is asking about how we know light is a wave. Okay, so it's got some key terms for us to include over here. So we know light's a wave for 3 main reasons. Okay, so light is a wave because it can reflect, it can refract, and it can diffract. All waves do those 3 things. Okay, so if you do those 3 things, it's a wave. Now we went into the idea of diffraction in a bit more detail with light, specifically laser light. So we fired laser light and we ended up with this pattern here. Okay, where you had a bright intense spot and it sort of lost its intensity the further and further you went away from the center. Okay, so there we go. So remember, we fired light at diffraction grating, and that was a laser there, and that's a grating there, and that, remember, made diffraction take place. That's a grating over here, just a million lines in there. So laser light diffracted and ended up with this. What actually happened that caused it to happen was you had each of these gratings acting as a source of light, and it caused the waves to interfere with each other. Okay, so remember, we had 2 waves like this, and we had the peak of a wave and the crest of a wave interact. You had a minima, and we had 2 peaks of a wave interact. You had a maxima. Okay, so you got a maxima here, minimas here and here, maxima there. So that's a big M, there, minimas there and there, and that's another big M there, maxima, but in the opposite direction. Okay, so remember, this ended up with this pattern here. We ended up with bright patches and dark patches. Okay, so that is essentially the idea of interference happening. So remember, these points over here are constructive interference, these points are destructive. So this is constructive here, so I'll just move my finger out of the way, that's constructive, these are destructive in between. Okay, so destructive is where you end up with nothing afterwards, constructive is where you end up with a lot afterwards. Okay, so path difference. So remember, if you've got 2 waves that are travelling different distances, so sorry, by the way, over here, in terms of the waves adding together, that's where the principle of superposition comes into it. So if you add that wave added to that wave, you end up with a wave of twice the amplitude, like so. Okay, but if you add that wave, let's zoom out so we can see it. So if you add those 2 waves added together, you end up with one of twice amplitude. If you add this wave add into it, no, wrong way, this wave, you end up with nothing. Okay, straight line completely. Okay, so constructive interference, superposition, destructive interference. So principle of superposition is the idea of the waves can add together. Okay, so the final thing is the idea of path difference. Okay, so if I've got a single source here, source of light, and it sends out 2 waves, okay, and they diffract and they meet, say, over here, this one would have travelled a different distance to this one over here, and therefore it will be at a different point in its cycle. So remember, by knowing how different it is in its cycle, you can figure out whether it's going to end up with constructive interference or destructive interference. So if it's pi, so if it's 2 pi radians, that's 360 degrees. That is a complete cycle out. So if it's a complete cycle out, you're fine, or an integer number of complete cycles out, you're fine. That will mean you end up with constructive interference. pi radians is 180 degrees, so that's half a wavelength out. So that's like the bottom scenario here. That's not the top scenario, that's 2 pi out, or 360 degrees out. These are 180 degrees out, they're half a cycle out from each other. So they're half a cycle out from each other. They're pi radians out. So you end up completely with destructive interference. Okay, that's what actually happens there. You end up completely with destructive interference. Okay, so you end up with no wave whatsoever. So the idea is you want to know how much further this has travelled compared to this. So if it's travelled a complete number of wavelengths further, you're fine. If it's travelled a complete number of half wavelengths further, you end up with destructive interference. What I mean by it's fine, you end up with constructive interference. So complete number of wavelengths further, you end up with constructive interference. If it's travelled a complete number of half wavelengths, that is essentially not. An even number of half wavelengths would be a better way. No, that's incorrect. An odd number of half wavelengths further, you end up with destructive interference. Okay, that's the idea. Now remember, upon reflection, you end up with a phase change of 180 degrees. So that's lambda over 2, or pi, phase change upon reflection. So if it came in like this, it would leave like that. Okay, so if this wave came in, it looked like that originally. As it came out, it would leave like that. Okay, so phase change 180 degrees. So remember, you're after an an odd number of half wavelengths if it's going to be out of phase and destructive interference essentially, and an even number of half wavelengths, or in other words, a whole number of wavelengths for it to be constructive interference. That's the explaining everything done. Let's get stuck into these questions. Okay, let's get the piece of paper out of the way. Oh, I've got a smiley face on that for some reason. I'll get rid of that one. I'm on to my line paper now. Right, okay, so, oops, daisy. So it's going to probably jump in out of focus in the line paper, so if I put my pen in the middle it won't. Right, there we go. So, first question on task 4. Wave A has a frequency of 120 Hz. Okay, complete the table to show the wavelength and frequencies of the 3 waves. Okay, so we've got some information. We've got the length of string and what it stretched between X and Y. Okay, so we need to figure out the wavelength by looking at the diagram. They haven't given us the wave speed, so we can't figure it out from there. We've got to look at the diagram to help us out. What if that is 1.2 meters? How much of a wavelength is that? Well, it's half a wavelength. Okay, so 1.2 meters is half a wavelength. That makes that 0.6 then for the 2.4 for the wavelength. So if the wavelength is 2.4 and the frequency is 110, we've been told 110 already. Well, if one of these doubled, the other would half. That's our ratio between these two. So the next wavelength, well, that's half a wavelength there. Sorry, that's a whole wavelength there. So that means the whole wavelength is now 1.2. So if we sort of list these out so you can see them easier. So it's going to be 2.4 meters, and that's 110 hertz. Okay, so if now we've got, zoom in slightly, too far. Okay, okay, so 2.4 meters and 110 hertz. So if the next one's 1.2 meters for the wavelength, because that is one complete wavelength, the whole of that there is one complete wavelength, what we'll actually end up with is that being 1.2 meters. That's halved, frequency must double. Okay, so this one over here, well, that's 1.5 wavelength is equal to 1.2, so let's get that really clear for us. So 1.5 wavelengths, so let's get this additional sheet out of the way. So 1.5 lambda is equal to 3 over 2 lambda is equal to 1.2. Therefore lambda is going to be 2 over 3 times by 1.2. So it's 2/3 of 1.2. So a third of 1.2 is 0.4, so it's going to be 0.8. We can see that already. We're just going to double check that. So 2 times by 1.2 divided by 3, 0.8. The wavelength of this one is 0.8 meters. Well, if we look at our wavelength, okay, from the original value, it's gone down a third. So that must mean if it's directly proportional, inversely proportional. If that's divided by 3, this one must multiply by 3. So therefore, that's going to be 300 and 30 hertz. Okay, it's a nice straightforward question starts off. So each of these waves has nodes at x and y. Explain what is points must be nodes, because they have no displacement. So nodes, remember, are points of no displacement. They're at fixed ends, therefore they don't move, therefore they're nodes. So similarity between the behaviour of A, an electron and a hydrogen atom. Electrons can be represented by stationary waves which fit inside an atom. Stationary waves have greater number of nodes present if the electrons and higher energy levels. Explain what is the case. Well, if you've got more nodes, so this one over here has 2 nodes. Okay, this one I've drawn here has 2 nodes. Let's draw another one underneath that now has 3 nodes. Sorry, it's got 3 nodes. Let's draw another one underneath that has 4 nodes, but in the same space. Sorry. 1, 2, 3, 4. The same space. This time 4 nodes. 1, 2, 3, 4, 5. Okay, let's say 5. I can't count today for some reason. 5 nodes. Okay. So this one has 5 nodes compared to the 3 nodes over here. So essentially what that's telling us is it's going to have a higher frequency if it's got a higher number of nodes. So higher number of nodes, it means it has a higher frequency. So if it's a higher frequency, more nodes. If it's got a higher frequency, we know from our photoelectric effect equations, higher frequency is related to higher energy. Okay, so therefore this means that if it's got more nodes, it'll end up at a higher energy level. So you've got to state E equals HF for that. Okay. So, explain what is meant by a transverse wave. You may use it to illustrate to help you answer. We know this from before. Remember transverse waves. In transverse wave, you end up with particle motion being parallel to the motion of the wave. Particle motion being parallel to the motion of the wave. I will draw a diagram and I'd label some of the key features in terms of wavelength and frequency. So give an example as well. So it's a good idea to give an example, e.g. light. Okay, let's have a look at some of the answers to these questions. Okay, so you can see our table is correct. Okay, nodes, no displacement, straightforward. Okay, then we've got nodes be shorter wavelength, momentum will be larger. Okay, so all reference to equals HF. So we did it via equals HF. The idea of momentum will be larger will come from the idea of the wavelength being smaller, and therefore the Broglie wavelength is smaller, so momentum must be larger for that to happen. But the easier way of saying it is equals HF. Right, so transverse wave, okay, is, okay, they oscillate perpendicular to direction of travel. Okay, so the particles oscillate perpendicular to direction of travel. Brilliant. Okay, so next question is asking about similarities, is asking about differences between standing wave and progressive waves. Remember, standing waves are used when we store energy. Okay, so they're just oscillating, so they're storing energy in the system there. Okay, well, progressive waves move from one point to another, they're transferring energy. Standing waves have antinodes, or points have a maximum displacement, while in progressive waves, all points end up with maximum displacement. As it moves through it, all points can have maximum displacement, while in a standing wave, only the antinodes will meet maximum displacement. Let me demonstrate it to you. Okay, standing wave, progressive wave. Okay, so progressive wave move through. If there's a particle, we choose there, and there's a particle, we choose there. So that will reach maximum displacement as this wave moves through it. Okay, so we reach maximum displacement there and maximum displacement there as this wave moves through it. Along here, only the particle here will reach maximum displacement, and the same at this point over there. Only that will reach maximum displacement because they're the ones that vibrate between the maximum points. Over here, in a standing wave, remember all of these have a constant phase relationship. Okay, these have a variable phase relationship. So there are your main differences between progressive and standing waves. Okay, let's have a look back at the question. There we go. Yeah. So we've got droplets forming at these points over here. So spiders are completely dependent on vibration transmitted through the webs for receiving information. The threads of the web are under tension. When the threads are disturbed by attract prey, progressive waves form and are transmitted along here. So you end up with a wave moving along here. And that means that stationary waves are formed. So standing waves are formed on here because of the fact the reflection at the end, therefore the waves interact with each other due to the fact they're reflecting too. So you end up with a wave interacting with its own reflection. So you end up with these points over here of no displacement. So that's what these droplets must be. So droplets are nodes, they're points of no displacement. Okay, the speed of the progressive wave sent by the trapped prey is 2.8 centimeters per second. Okay, use a diagram to determine the frequency of standing wave. Well, this is tricky because obviously this could be to a different size for you guys. So it says 1 centimeter on the diagram because it's 0.25 centimeters of thread. That isn't useful for you, so sorry that I've shrunk the picture and the paper, but let's just see how they figure it out. So we've got speed. You can use the idea of nodes to figure out the wavelength. So remember, if there's two adjacent nodes, that's half a wavelength. So the distance between a node, so if we've got, let me just draw a standing wave, or I'll add it to the standing wave. There's one node, there's another node, there's another node. The distance between two adjacent nodes is half a wavelength, therefore a node, skip one, the next node, that's a whole wavelength. So you can figure out the wavelength from the diagram. You've been given the speed, so you just rearrange for frequency. The speed, remember, was 9.8 centimeters per second, so you need to convert everything into meters. Let's just show you how they've done that. So 21. Here we go. Okay, so V equals F lambda. Evidence the wavelength is twice the node to node distance. That's what I'm saying. So node to node is half wavelength, therefore we need to double that. So it gives you what the wavelength is, and therefore you can figure out the frequency by using the speed equals frequency times the wavelength. Okay. So next one. Okay. State two conditions necessary for total internal reflection to occur at the interface between air and water. Well, the one that we always know about is about the critical angle and its relationship to the angle of incidence. But there's also another one. Okay, you've got to remember about the direction that's going from less dense to more dense. Okay, and this is one thing that I hinted at in class. Well, I sort of stressed in class the fact that we've got to be talking about the right direction in terms of density. Okay, so they're always the two things they talk about for that. So to prove that, I bring that point up. Here we go. So direction needs to be of light needs to be from water to air. So that's again talking about density. That's more dense to less dense. That's what we're talking about there. And the angle of incidence therefore is greater than the critical angle. So I needs to be greater than C, and it needs to be going from water into air. Okay, for that to take place. More dense to less dense. Okay, for total intensity to take place. Okay, 23. Okay, so name the process of light changing direction this way. So that's refraction. Remember, refraction takes place due to a change in speed of the waves. That's the next part of it. Explain what it's supposed to take place. Change in speed due to a change in medium. Okay, so medium just means what it's travelling through. So different media, I should say, really, plural of medium. I mean, it's travelling through a different substance. So diagram shows fish looking at a butterfly. Is it fish looking at a butterfly? Diagram represents some fish under water and a butterfly above the water. Draw a ray diagram to show the path of light travelling from the butterfly to the fish's eye. So the fish is looking at the butterfly. So there's two potential routes. You know it's going to refract as it hits the water. You've got to think which way it's going to refract though. So you might think it goes this way and then over to there. Okay, we might think it goes this way and then over to there. Well, you've got to figure out, as it goes into the water, is it going to slow down or speed up? Well, think of it in terms of, let's just draw it over here. So you go, oh god, I'm going to have to draw a butterfly now. Oh, GCSE art, I didn't do it. Okay, here we go. There's our butterfly, how wonderful. And there's our fish. There's the boundary. Okay, so as the light comes in, this side of the light, okay, it's going to hit the water first, so that slows down first. This side's going quicker, so if this side's going slower, it's going to bend in this direction. Okay, so it must go like this. Okay, it must go like this. It can't bend this way and go across. It must bend in the direction of sender. It's always a good idea to draw in the normal as well, just in case. So the normal is drawn at the boundary, remember. So explain what is meant by the critical angle. So remember, the critical is the key definition. So again, I want to show you from the mark scheme. Okay, so only 2 marks, so it's pretty straightforward. But it's the angle at which total internal reflection begins. Okay, or it's 1 over this. It's 1 over. So it's 1 over. Let me get this right. The refractive index is equal to 1 over sine of the critical angle. So the sine of the critical angle is therefore equal to 1 over refractive index. So inverse sine of 1 over the critical angle tells you, so 1 over refractive index, so it's a critical angle. So critical angle is the angle at which total internal reflection takes place, but it's also the inverse sine of 1 over n. So you can see what that was tricky to say out loud. I'll just bring it over there. So you can see what that was tricky to say out loud. You sort of think your way through that to make sure you get it the right way around. So refractive index is 1 over sine c, with c being a critical angle. Therefore sine c is equal to 1 over refractive index. You can rearrange for c and say that C is the inverse sine of 1 over the refractive index. So remember, n is the refractive index there. That's just a value that tells you how refractive a substance is. So what is my crystal angle? Okay, identify the angle that identify the angle as that is in the denser medium and indicate this is the maximum angle for refraction or total refraction occurs beyond this. That's what we were saying. So they don't really need this point here, but it's that point over there that's a key one. So remember, it's an angle in the denser medium is the key point. The angle is inside that denser medium, so it's an angle for the medium that's actually causing this refraction to take place. Okay. Right. Next. This is quite a tricky question, this one. Okay, so I remember this coming up on a paper. I know a lot of students struggle with this one. So the next one's 4 marks. So I don't know why I gave such a small amount of space for this. So explain how rays from fish A would reach the eye of fish B along 2 different paths, and add these rays to the diagram to illustrate your answer. Well, there you go. That's why I only added a couple of lines, because most of it's from drawing the diagram. So the first idea is that you're going to get a beam of light that literally goes in a straight line across from A to B. The second one is going to reflect off the surface. Remember, there's going to be a phase change that occurs, and then it's going to go over to there. Or there may go, it's going from more dense to less dense, so actually there won't be a phase change. It's going to go across like this, and then come back. So one from reflection and one from that. Remember, there's a path difference between those 2 paths, so that could lead to some form of interference possibly. Okay, let's see what the mark scheme says. So direct path because of no change in medium. Okay, so straight line across. Angle of incidence is greater than critical angle. Okay, so direct ray drawn with arrow. Okay, so you got to put an arrow on it. Total to reflection passes path correctly drawn with arrows. So that's the idea of one reflecting, one going straight through. You've got to get the arrows on there. Very straightforward. Okay, 24. Here we go. So explain what is meant by the superposition of waves. So remember, superposition is when waves are adding up, either by constructive or destructive interference. So adding up or taking away. And remember, it's all to do with the amplitude and frequency and wavelength of these waves that cause this to happen. So with vibrations from 2 waves, all waves from 2 sources, coincide at the same position. So we'll do that add up. So the resultant displacement is the sum of displacements due to individual waves. That's a definition I've given you in class. So look back at your definition of superposition, and that is a definition of superposition. So when vibrations or waves from 2 or more substance sources arrive at the same point, or coincide at the same point, and that leads to a resultant displacement which is equal to the sum of the individual displacements. Okay, so how are standing waves formed? So remember, you've got to have 2 waves for standing waves to be formed, and these 2 waves need to interfere with each other. Superposition needs to take place. Now, it can be 2 waves or a wave interfering with its own reflection. So the idea is the waves need to be travelling in opposite directions, and then superposition needs to take place. So whether in phase, you end up with constructive interference, in other words, antinodes, maximum displacement, or whether in antiphase, you end up with destructive interference, in other words, nodes. So that essentially causes the point of no displacement. Okay, so 3 pretty straightforward marks from that. Alright, next. So a standing wave is visible on the micrograph between atoms A and B, so that's on here. There are nodes at X and Y. The dark lines between X and Y show antinodes. Okay, so nodes at X and Y, the dark lines in between show antinodes. The distance between points X and Y in the micrograph is 4.2 times 10 to the minus 9. Let's write that down. That's going to be a number we're going to use. 4.2 times 10 to the minus 19, in other words, nano meters. Use this information to calculate the wavelength of the electron waves. All right, okay, nice tricky question. So A and B, both of these are antinodes. Both of these, there are nodes at X and Y. So X and Y aren't nodes. X and Y are nodes, yep, there we go. So we've got a node there and a node there. Is that right? There are nodes at X and Y, yep. The dark lines between, let's move this over, it's getting in the way. Okay, so nodes at X and Y. Dark lines between X and Y show antinodes. Okay, so we've got nodes at X and Y. So we've got a node over here and a node over here. No displacement. Okay. Dark lines are antinodes. So there's 1, 2, 3, 4. Now I'm thinking there are 4 there. Okay, obviously this picture will be a lot bigger in the exam, so I'm thinking there are 4 antinodes there. I might have that wrong, but we'll see. So there's 4 antinodes in between. So there's 4 points of maximum displacement. Okay, 2, 3, 4. So let's draw that wave in now. Okay, so you can see I've put my 4. So it's not a very consistent wave, but that's not the important thing. So I've added my 4 points of 4 antinodes in, points of maximum displacement, 1, 2, 3, 4, and then I just drew the rest of the wave. Okay, so there's my, let's bring the light again slightly. Okay, there's my wave poorly drawn that shows me what's actually taking place. So now we know the distance between x and y is, so that distance there is that 4.2, so just label that up there. Okay, use this information to calculate the wavelength of the electron wave. So that's 1 wave there, 2 waves. There's 2 waves, so we divide that by 2 essentially. Is my thinking. Here's where I've got it wrong, I'm guessing. Right, okay, so we divide that by 2 and that will tell us it's 2.6 times 10 to the minus 19. Let's have a look. Why am I saying 2.6? 2.1 times 10 to the minus 9. I said 19 as well, didn't I? Yes, 2.1 times 10 to the minus 9. Yeah, it is. Look at that. Yeah, it's 6:30 on a Wednesday. It's the middle of the week. You can allow me to make a small mistake like that. That's fine. So you can see that over here they drew it out as nodes, antinode, node, antinode, node, antinode. Okay, but you don't need to do that. You can do it the way that I did it. If you find this easier, drawing that diagram there. Okay, that's cool. But there's your node, antinode, node, antinode, node, antinode, node. Okay, so you can do it like that if you wanted to. But I picked it out from the diagram that there were those nodes, that antinodes that were there, the 4 antinodes, the bright patches that were there. Okay, where are we? Okay, so tricky question, nicely done. Explain the meaning of the terms amplitude and antinode. So remember, amplitude is the height of the wave from the middle of the wave, and antinode is a point of antinodes are points of maximum displacement, maximum amplitude, antinode, points of maximum displacement. Okay, so a ray of light travelling strikes the middle surface of a plate of equilateral glass. Okay, state what happens to the properties of light as it goes through glass. You just need to know these. Okay, the speed is going to reduce as it goes into glass. You know that straight away. Okay. You also know that the colours of light are in there, so we've got to think about what actually defines colour, and it's frequency that tells us the colour. So frequency must stay the same, and the wavelength must change. So by V equals F lambda, okay, if that goes down, well, that stays the same, wavelength must go down as well. Let's double check that. Yeah, frequency isn't altered. Okay, the other 2 decrease, just like I said. So remember, the frequency decides the colour. The frequency is why we have all the colours that we have. So the frequency is not altered at all in the slightest. However, the wavelength will change and the speed will change. Okay, brilliant. I think that brings us to the end of this ISP. 225. Yep. Okay. So just one more video left for this ISP. And if you've already done the ones on DC electricity, that'll be all your ISP tasks for Unit 2 done after the next video. Thank you very much for listening, guys.